Get into what needs were identified in terms of research in this area and environmentally benign manufacturing. We could summarize, and I think we only have time really to talk about metals, and we talk the most about metals this term. So we'll just summarize there. We had a subgroup here of individuals who were involved. You see some folks from industry here. The big three are represented here. Some universities, government, EPA, and National Science Foundation, all represented here. And we basically sat down for a couple days. And it's not feedback. All right. Not sure what that was. I don't have a cell phone on me. Okay. Anyway, we sat down to talk about trends in the industry. Okay. And one of the big trends that the automakers noticed or brought to the floor was that they're really trying to get out of hard manufacturing. They just want to be assembling and designing, right? That's where the most value added is, right? Where they can get the most return on the dollar that they put into it, right? So we talked about the smart car, which is an extreme example of this. You just set up a campus, right? And now you've got different companies coming in and having some operations, and really it's a hub where all the assembly comes together. There was a large degree of uncertainty identified regarding where products would be going, right? We've got hybrids now. We've got all sorts of alloys we can be using in the chassis. We've got fuel cells coming online. And more niche demands from consumers, right? So more variety in vehicle applications, right? So a lot of uncertainty they identified from the design standpoint, right? The only thing that they could identify as being certain was this push, the squeeze on the suppliers, right, towards lower cost, increased fuel efficiency, and environmentally benign manufacturing, right? Again, thinking life cycle. These folks thought the IC engine was going to be around in some form for the next 10 to 20 years. So we could talk about fuel cells, but this is probably dead-on accurate. In more trends, the evolving business model, leasing, service-oriented products. When you have leases, you got products coming back in a form you can predict relatively well. Then the service-oriented model can come to the fore. Reconfigurable architectures, reconfigurable manufacturings. Right? We talked about the high wire. This was the GM concept car, and the fuel cells, right, where you're able to change the top. Right? I know. One of the other automakers is also working on dressing the car up, so you can basically take an ordinary vehicle, steel vehicle, and put some magnetic material over it and actually get it to look a different color, even change the lines a little bit. Built to order, right, more niche production. We considered a lot of things in a couple days, cross-cutting issues, materials and processes, joining, forming, machining, freeform fabrication, casting, powder metallurgy, and inspection. But the overarching theme was what we've already talked about. I think the top two we've mentioned over and over again. The need for national priorities, not the need for any given company or designer to be setting environmental objectives, but for us to set some direction at the national level as a society, and now partition those priorities into different industries and get everybody on the same page, essentially. And then to provide tools and data for life cycle design support, right? What are the top priorities for a car, right? What is it in manufacturing, and what is it about the design, right? To enable designers to make these trade-offs. Those tools and data are largely unavailable. Process integration, hybridization, elimination. We've talked about net shape operations, eliminating downstream operations. That's what this point speaks to. But supply chain relationships, especially as you have now decentralized manufacturing. What are the environmental impacts? Are you pushing environmental impacts now? You're essentially divesting yourselves from environmental impacts, right? So the supply chain relationship and understanding the impact of a given design on the total life cycle environmental impact of a product is going to get more difficult, right? And education at all levels, right? What is the environmental impact? Tends to be lacking. Okay. So I don't think these are really prioritized. This is just a list of priorities. It's not necessarily in an order. We can start with life cycle system design, materials, material selection, manufacturing, recycling, of course. Net shape casting. I'll say more about casting in just a minute. Effluent-free machining. We've talked about metalworking fluids. That's what this point speaks to. Making them minimizing energy consumption, especially in welding. Metalworking tribology, engineering surfaces, right? If we could get cast surfaces with good surface properties, then we wouldn't need to necessarily go to a grinding operation downstream or an EDM, electrical discharge machining operation downstream. So better understanding tribology. Most of our engineers, there's a very specialized few that really understand tribology. In the surface operations, we could talk about plating, right, getting the effluents down, trying to minimize the use of toxics and energy in these processes. Air emissions and materials used in casting. Talk about casting again in just a second. And disassembly of permanent joints. We talked about these reversible snap fits before. What if? Would make disassembling a vehicle a lot easier. Okay, on some timelines. You can see very little we expected to get done in the next 5 years. I mean, the point is, where you are in research now says a lot about where industry is going to be in 5 years. And there isn't much research going on. It's not a heavily funded area. In the 5 to 10 year range, we're hoping to get some funding in the next 5 years to do some of this work. But again, the slope's in the wrong direction. This was 2-3 years ago, 2 years ago now. And a lot of this research hasn't even begun. So we can get in a little bit deeper in terms of the processes themselves. Materials, again, these have come up in different forms already, right? Alloys for optimized performance. You can lightweight a product by going to an alloy, but when does that make sense? And is that alloy really castable or machinable? What are its surface processes going to be? We could talk about recycling aluminum. You know that recycling aluminum is a good thing, but the alloy of aluminum, it turns out that aluminum recycling is very sensitive to the alloy. So they're not as recyclable as mixed materials as one might otherwise imagine. So sorting and purification become quite important. And the design system, again, this gets to education, understanding the materials and the implications of material selection. One guy there, he's a big fan of structural foams, very lightweight foams that would be of more polymeric sort of material, very low energy in terms of what's embedded in these foams, and then for transportation products. And this workshop was pretty much exclusively focused on transportation products. Probably be a good application, but you don't see too much structural foam in auto products. Okay, getting into casting a little bit, net shape casting, great. If you could just sand mold a Buick, you'd be in great shape. But of course, we know it takes more than that. Precision is an issue. Casting, especially sand casting, doesn't get you very good dimensional tolerances, at least relative to what we need in today's highly engineered products. More precise and accurate molds be a research area. Being able to predict distortion, we don't have very good mathematical models of this. And the surface finish, as I've already mentioned. Optimizing gating. What's a gate? We got any casting people in here?
It's what allows a metal or plastic to flow into a mold.
Bingo. Right? So some of the metal or plastic's going to freeze up or solidify in the gate, right? And then you're just going to have to chop that off and then grind it down and get the surface finish behind it. Right? So optimizing the gating to get reduced scrap. I mean, we could talk about casting as an engineered scrap or engineering scrap operation, right? Because it's planned in. You know you're going to have it. Right? So in that sense, it's wasteful. Better mold coatings for sand molds. Get the sand to last longer, improve the surface finish, minimize downstream operations. Again, it's the theory there. Improving thermal efficiency. Can you recover the heat, right, instead of just wasting it? Or can you have continuous casting? You're making steel. You've got refined alloys. Can you just go straight to the product, right, without a solidification and remelting step? All things we could be thinking about. And these are for the non-casting experts here. It's an example of a product in the upper left. Just because we didn't have usually I give a whole lecture on casting, but This year we're not doing that. But suppose we're making this part up in the upper left. It's a hollow part. It's got some flanges on it and an elbow. How would we get from design to part? Well, we start with some prints, right, that are going to take on the exterior form of the product. The cope is the top and the drag is the bottom. So you see that what we're going to do is we're going to be a good example here of the cope. Now, the cope's going to end up on top. We can take that cope and we're going to put basically a flask around it and pour a lot of sand in there and ram it down and make sure we've got a sprue, gates then, and a riser. What are the risers for? Do we just have one casting expert here? Or?
It's like for including material that, like when the casting is solidifying, it basically shrinks down so it can get some molten material to fill out.
Exactly. So it's back pressure, essentially. So the idea here, as was mentioned up front, is you're going to pour the metal into the sprue here. It's going to fill up the part, but as it solidifies, it's going to densify, right? And if you don't have excess material now, you're going to have voids. So basically, you'll fill up the risers too, and as it cools, now some of that material will come down. It also helps the residual stress characteristics. Now, this is a hollow part, so you can't just let it be solid metal. So you're going to need to make a core. And now you'll have a core box to do essentially cast out a core. But this core is likely to be sand. It could be other materials too. It's not going to be the same sand, though, that you would use in the casting, because this is actually going to have high pressures on it. So you'll have to chemically bind that sand. It's not just green sand. It's chemically bound sand. And that, of course, now you'd say chemical bound sand. What are the chemicals? They're chemicals that end up in releases of ammonia and formaldehyde and other organic, respiratory organics, in particular in the casting plants. It's nasty stuff, especially when it heats, right? So this is going to be under intense heat and pressure. So that those gases are going to get out, right? And that's why casting plants are regulated but are still quite nasty. So we've got a core. Here's the cope. So we're going to basically pound the sand in over the top of it. You can see the holes here for the risers and the sprues. Here's the drag. The bottom half, you're going to pack that with sand, then flip it over, place the core in it, assemble the cope and drag, pour the metal in, shake out the sand, knock off this sprue and gates here, and the risers, and we are arriving at a finished casting. Okay. So that's the process. Of course, you got to handle the sand, right? Here's what it looks like from a facility standpoint. An artist's rendering, I suppose, to imply that it's not the cleanest operation. Right? You see these fumes, right? A lot of electricity here. You're melting scrap metal or virgin material here with some coke and fluxes here to help densify the metals. Right? Melt that down. You've got a pattern-making operation, some sand for the cores. You've got some casting sand here. You've got now the assembly of the casting itself, the pouring of the metal, shaking out the sand, hasn't really shown here anywhere, but it's a big part of the process too. Cooling and cleaning and shipping. Right? So you get the idea. When you hear about casting, you're probably thinking about sand. There are other forms of casting. Energy consumption, right? Fluxes, electricity consumption, perhaps depending on the type of furnace you're using. Air emissions, especially respiratory organics, volatile organic compounds. Think about water wastes, because you're going to clean the sand, and you've got to keep dust down as you're handling the sand. So there'll be some water emissions, organic emissions in the water. Okay. So these are some of the pollutants, okay? And there are other forms. It's not just sand casting. This is investment casting. Anybody familiar with investment casting? Anybody want to explain it? Can you see it from back there?
Yeah, I can see it.
What's the basic idea?
I'm familiar with it, but I don't
You've heard
remember what the difference is between it and regular casting. I know I should know.
No sand. Well, okay, there could be sand, but It's not sand in the same way.
The pattern is basically dispensable.
Yeah, the pattern is disposable or lost or invested, right? That's the big difference here, because you just had a hole or a cavity that you're filling metal into. Here you've got a formed part, maybe it's wax. Now suppose we're making this part, I don't know what it is, some type of a elbow or connector piece, and we can basically make several of them on a tree. And this might be wax to start. So what I could do is put a flask around, and this is one way to do it, put a flask around it, and I could fill it with a material. It could be sand, or it's a refractory substance that's not going to be disturbed by the addition of molten metal. So what I can do now is fill it up with a refractory material, right, and essentially melt out that wax or plastic. Now I've got the hole, and I can pour the metal in, shake out the refractory, and then basically cut the tree down, machine it, grind it, get it ready to go. That's one way to do it. Another way to do it is just to dip the tree here into a refractory slurry, right, and make sure to coat it really good with that slurry, and basically do the same thing. So you're just doing it without the flask, right? But same idea. In this case, actually, when you melt it down now, you're going to lose less material. You fill it up essentially in the same way and machine it down and send it. Okay. But imagine now, I mean, of course there's going to be emissions. Whatever you make this tree out of, the wax or plastic, whatever it's going to be, that's going to become air emissions now, right? How do you handle the refractory? How much of that material are you going through? These would all be questions. There's die casting. Oh, I'm sorry, one more, lost foam, right? Foam, styrofoam, styrene, right? Here's a pattern, right, that's probably cylindrical, just seeing the cross-section here, right? You can put sand around it, right, and basically do the same thing. This is essentially an investment casting, but that investment's going to be that of foam, right? So now you've got styrene vapors, right? And you can see some of the health issues involved. Again, still the energy, still the sand. Right? Die casting is another form, right? I think most people are familiar with die casting. You have the cold chamber process or hot chamber process here, right? So you can see why when you talk about environmentally benign manufacturing, casting tends to come up quite frequently, right? And people want to avoid casting, or if you need to cast, then at least stop it there and try to avoid downstream operations. Okay. Forging and forming, right? Here it boils down to energy consumption and lubricants, right? You may be familiar with deformation processes. You have drawing operations here, right? Where do the pots and pans you use in the kitchen come from? You know, it's these types of metalworking operations. Drop forge, you may be familiar with drop forge tools or cold work tools. You can have this here as a crankshaft, right? Again, it's an engineered waste product, right? Because you're basically beating your parts into submission, you know, in a series of steps, right, to get to your crankshaft. But you've got some flash here that's going to need to be removed. And you can do that in an intelligent way, right? You can design the part to minimize the waste or the energy that you have to consume in a forging. Right? These are huge presses that do these jobs. Right? And you need types of conversion coatings and lubricants that are not unlike cutting fluids. They're just more concentrated forms of the oils and fats, and sometimes you need to use acids. We talked about conversion coating to apply these types of lubricants to surfaces. These are the exact operations that you would use them in. Okay. Conventional machining, we'll talk a lot more about metalworking fluid. Well, maybe we will, maybe we won't. We've talked enough about it already this term. But just to make sure that we have, you know, a visual of what these operations is. This is turning. What's the idea of turning?
The lathe.
Okay, that's the machine you would use. So a lathe performs a turning operation. But what does it do to a part?
Takes material off.
Yeah, in a
Takes
circular
material off.
manner.
There's machining. It's a metal removal process. Can you use square parts with it?
So.
Not unless you want them to become circles.
Yeah, exactly. I mean, the whole idea, it's radius reduction in general. And yeah, I guess you could tolerate a little bit of a square in here, but not too well. Normally you're just taking round billets and bringing them down, or ingots cast as round, and bringing them to a reduced diameter state. All right, here's drilling. We're all familiar with drilling. What's different from a coolant and lubrication standpoint about turning and drilling? Anybody want to fancy a guess here? Which one requires more lubricity?
I would say drilling.
Why?
Because you're going inside the part.
Yeah, there's nowhere for the heat to go.
Right.
Nowhere for the heat to go? Yeah, so one's more of an external process and one inside, and that's exactly why the fact that you're going into the part matters. And what else?
The little shavings have to get out.
Yeah, they need to get out. So you need some pressure and you need some lubricity, right? So a lot of times you end up taking the coolant in through the spindle itself, right? And that provides pressure and lubricity to get the chips out. And you may go through, especially in a gun drilling application, it's often found in auto. They call it gun drilling, how you make a shotgun, just very long and deep, but still relatively low diameter hole. Chips really got to get their way out. So the coolant under very high pressure, very high volume application rates, you go through coolant, like water. Milling. All right, so from the terminology, we're just used as an external process, generally profiling here, as you can see. Grinding, a little bit different. It's external, but you're basically trying to get very good surface finish here. Right, so you've got negative rake angles here, as they would be called, under at a lot of different contact points. So lubricity is very important. Often you'll use just a straight oil. There's a project a colleague of mine and myself we're trying to start up now with an auto manufacturer on grinding, trying to get away from use of straight oils in grinding and trying to recover chips from it, because it's a grinding process for camshafts, and they're not even recycling the steel because they don't know how to separate it from the oil. We think we can do it. In fact, we think seniors in our design class can do it. So we're going to try to make a senior design project out of this next semester. This is electrical discharge machining. It's a form of machining that doesn't get talked about enough, but it becomes more and more important. High precision, high surface finish, or very, very good surface finish. You can get that from electrical discharge machining. It's basically creating lightning at the mesoscale or micro scale. You've got you're basically got a gap with dielectric fluid. Oil is a great dielectric. So you create, static electricity. You're creating lightning, right? And so you get discharges at a relatively high rate. Actually, in terms of machining process, it's very slow. But you've got dielectric fluid. You've got all kinds of electrical discharge machining going on here. I've got a proposal into the National Science Foundation right now to look at the environmental characteristics of this process and relate it to other ones, because we're using it more and more with higher precision needs, tighter tolerances, or parts in contact. We're using more and more electrical discharge machining. What are the implications for the environment? They can't be good. We would like to quantify them and bring them out to the light and figure out how we can. Dielectrics are recovered, but the handling process is rather energy intensive, and separating out the materials. Can we get the chrome or even the steel or whatever the part is? Can we get those metals? Can we recover those metals? Right now it's hazardous waste. Okay. Another honorable mention here is electrochemical machining. It's different in that you've got now electrodes in the presence of electrolytes. So you're basically creating microscale redox reactions, oxidation reduction reactions. And you're taking, instead of blasting using electrical charge a metal off, what you're doing is chemically removing it by creating a redox reaction in the presence of electrolytes. This is more of an aqueous salt type electrolyte. Again, you're still going to have metals in there. And in this case, it's going to be much more soluble metals. So you'll get soluble metals to some degree in the other. But because you've got aqueous solutions, you're going to have now metals and water that you can't necessarily remove easily. You can't just let them settle out. But if you look at these micro turbine blades, it's pretty cool. I mean, you can't machine that. And the residual stress characteristics are really good. Right, so you don't have residual stresses here. Okay, so, oh, that was cool. Didn't mean to do that. Wow. We've talked about freeform fabrication, right? The production of the M, that's why I put it there. That was our case study. We talked a lot about additive versus subtractive manufacturing, and that's where I had my aha moment, because I've got a colleague down the hall who's one of the